All right, let's continue with oxidation reduction. We defined what oxidation reduction is in our previous video. You gave some examples. Again, key to get proficient at assigning oxidation states and numbers so that you can decide what's being oxidized and what's being reduced. Now we're going to give you some characteristic reactions. And again, these are things that you need to be able to recognize. So notice the subtitle there, oxidation of metals by acids or salts. Oxidation of metals, what does that mean? It means the metals are what? Giving up electrons. Okay. A very specific type of redox reaction is called the single displacement. Let me show you what that is. In this reaction, it turns out that the metal can give up its electrons to another metal cation or to the hydrogen cation, the proton. All right, and we'll show you examples of both of those. All right, here's the general pattern with metals. Now we're going to talk about metal cations. You've got some neutral metal, some initial metal that's free. It reacts with another metal cation. Okay? Remember, metals exist as neutral elements or cations. You will never see a metal gain electrons and have a negative charge. Okay? And essentially, all that happens is the electrons from one metal are transferred to the metal cation. And now you've got metal 2 as a free element and the first metal as a cation. So let's look at some examples. Okay? So we say metal 1, in this ACX example, metal 1 is being oxidized by metal 2 is being reduced by metal 1. Okay. All right. Here's a specific example. Copper metal reacting with silver nitrate. Remember when we have that AQ there, that means that we've got the silver ion floating around in solution, the nitrate ion floating around in solution. Right? But there's our metal cation, the silver plus. Okay? All that's happening here is the copper says, take my electrons, the silver cation says, I'll take it, and we end up with the silver metal, and we have developed the copper to cation, which now, because of the charge, is soluble and can float around in water. Okay, this is what it would look like. Right? In this picture, we're showing copper metal, which is this wire. I'll do this, the wire, right, in a solution of silver nitrate. If you let it sit over time, what happens is the wire actually starts to look fuzzy. And what that is the silver is actually plating out on the copper wire. And you also notice, somewhat faint, but the solution has turned a sort of light blue. And what is that from? Well, it's from the copper cation. Copper 2 cation has a characteristic blue color. So again, we've reduced the silver cation to a silver metal, and you see it plating out on the copper. Single displacement redox reaction. All right. How about with an acid? We said that one metal can give up its electrons to another metal cation. What about a metal giving up its electrons to H+? All right. Well, here's a general pattern. One metal with an acid. All right, so let's say HCl, and the metal is going to give up its electrons to the proton in there and create hydrogen gas. It's a very characteristic reaction, plus the metal cation is left over. All right. We say that the metal 1 is oxidized by H+. H+ is reduced by metal 1. So before we move on, I wanted to remind you, and this was mentioned in one of the previous videos, that water itself can act like a weak acid. Remember the distinction between strong and weak acids. Okay? And we write it this way. We call this autoionization of water. In reality, the accurate way to write this is so forth. Remember, protons actually don't exist. It's the hydronium ion. All right? Because water is a weak acid, water can actually participate in this single displacement reaction, meaning that the metal that's present will give up an electron to the H+ in solution. So let me show you how that works. Sodium metal. It has to be an active metal, and we'll define this in a minute. What do I mean by active? Active metal means something that really likes to give up electrons. Okay, you've probably seen demo videos of someone throwing sodium or potassium metal in water, and it reacts violently. That's because it's giving up its electrons. So sodium in water, which acts as your acid, generates the hydrogen gas plus sodium hydroxide. So you've gone from neutral sodium to the metal cation. Okay. It's given up its electrons. Who has the electrons? The H+, which is reduced to hydrogen gas. Okay. Let's talk about this exchange of electrons between one metal and another metal cation. All right. And what's this reaction showing right here? Now, this is our copper-silver reaction before. Let me remind you, we had copper, neutral copper, and the silver cation. And all that happened was the copper gave up its electrons to the silver cation. We now have copper 2+ and silver solid. All right. What is a spectator ion in this, by the way? Well, it's a nitrate. If you do a complete ionic, net ionic, you would cross out the nitrates, and therefore you've got that. There's your net ionic reaction. So basically what I just wrote above it. Okay. Let me ask you this. Why doesn't it go the other direction? In other words, what is it about copper and silver that says that the copper is going to give up its electrons and the silver cation is going to say, I'll take them and I'm not going to give them back? In other words, question mark, why, if I had silver metal, say I had a piece of silver metal in a beaker of copper 2+, why would that copper 2+ not grab the electrons from the silver metal and go in this direction? Well, we need to talk about the activity series. Okay, so we mentioned that metals like to give up electrons. That's not an absolute, meaning that as you move from the left side of the periodic table to the right side, the metals are less and less likely to give up electrons. Hence, the most active metals are on the far left side, the group 1, group 2 metals. Those are the ones that say, take my electrons. Okay? So our next video is going to be talking about the activity series.